Welcome to this lesson on Raoults Law. This is going to be an introduction to a preliminary form of Raoults Law. So we want to talk about gas and liquid systems, and for this lesson we're only going to refer to ones where we have just a single condensable component. So we frequently are going to talk about saturated systems, and usually by that what I'm meaning is a vapor-liquid coexisting. Now, saturated systems might also be solids and liquids or any other number of things. But typically in chemical engineering classes, if we get lazy and just say it's a saturated system, we usually are talking about vapor plus liquid. Now, this doesn't tell me anything about how much liquid and how much vapor. I might have one drop of liquid and a whole bunch of gas. I might have one bubble of gas and a whole bunch of liquid. But I might have something where it's, closer to being equal part gas, equal part liquid. If my substance was pure and I had this saturated system of vapor and liquid, then I would say that it was at its vapor pressure. But let's talk about systems where I have more components, not just a pure substance. So, if I have vapor and liquid and I have two phases, Gibbs phase rule, if I have no reactions and two phases, says that the degrees of freedom is 2 plus C minus those two phases minus 0 reactions. And so I end up with C, the number of components. So I'm going to need to specify as many variables as I have components according to Gibbs phase rule. So that's one thing that I need to know. We're going to look at one simple form. I'm going to only have two components for now. And I'm going to look at a simplified form of Raoults Law. Now, this is not the general Raoults Law. This is a simplified special case . Okay, it's going to be valid if I have two components and if I only have one species that would condense. So what Raoults Law says is if a gas at temperature T and pressure P, okay, so two components, I'm specifying two things, contains a saturated vapor with mole fraction Yi, telling me how many moles of component I in the vapor per moles of total gas. And this vapor is the only species, so I is the only one that would condense if the temperature were lowered slightly. Then the partial pressure of the vapor in the gas equals the pure component vapor pressure of I at the system temperature. So frequently we think of this as air plus water vapor, right? That's a gas. We'll call air a pure component, and then water is my second component. So this would, in some sense, be two-component system, okay? And if I cool my air with the water vapor in it slightly, this will drop out as little liquid droplets, but the air is just going to stay in the gas. So this is the sort of system that we're talking about here. And what Raoults Law says is that the partial pressure of the vapor in the gas for the one that's going to drop out as a liquid, for this guy, the partial pressure of, let's say, water in this case, and we know that that means it's the mole fraction of water times the total pressure. The partial pressure equals the pure component vapor pressure at the system temperature. So it's equal to the vapor pressure of the water at whatever the system temperature is. Now, this is good for the water. It's not true for the air. It's only going to be true for the one that can condense, that will form this little drop of liquid, okay? And it doesn't need to be air and water. It can be any number of systems. But if I have only one that can turn into a liquid, Raoults Law is an easy way to describe the system. So let's look at an example. In this case, I have MEK, methyl ethyl ketone, and nitrogen. The system is at 45 degrees C and 1,060 millimeters of mercury. So I've specified I have two components, And so therefore I have specified two intensive variables, temperature and pressure. In this case, nitrogen is not going to condense. This, however, the MEK, will condense. We want to determine the composition of the gas phase and the partial pressure of each component in that gas phase. Okay? So I have temperature and pressure. I've got my two things specified. Nitrogen is not condensing, so I know that Raoults Law is going to apply to the MEK. So it says that the partial pressure of MEK, which we know to be the mole fraction of MEK times the total pressure, is going to equal the saturation pressure, the vapor pressure of MEK at the system temperature, which in this case is 45 degrees C. So I know this, right? This is 1060 millimeters of mercury. I'm looking for this. I know the temperature, and I can use something like Antoine's equation to find the vapor pressure. That will allow me to find Y for the MEK. And I know that the sum of my Y's has to equal 1, so therefore Y for the nitrogen is going to be 1 minus Y for the MEK. An alternative form of this, remember, is for partial pressures. Partial pressures, the sum of those is the total pressure. So the partial pressure of nitrogen will equal the total pressure minus the partial pressure of the MEK. So that outlines what we're going to do in our solution. So finding the data in the appendix of the textbook, I found that at 45 degrees C, the vapor pressure for MEK was 218.2 millimeters of mercury. And you should take the time to go into the appendix and confirm that you also would get these numbers. Okay? It's possible I get the numbers wrong. Okay? I don't always hit the buttons on the calculator perfectly. So if I have the vapor pressure and I have the total pressure, I can solve for the mole fraction of MEK in the gas phase. So Y is going to be used to designate the gas phase for MEK with that subscript there. And I find that it's going to be 20.6% MEK, and the rest of it, 79.4%, will be nitrogen. The partial pressure is the same as the vapor pressure, so 218 millimeters of mercury. The partial pressure of nitrogen is the total pressure minus the partial pressure of the MEK, so therefore 842 millimeters of mercury. Now I would like to make a few comments on this example. So one of the things that first you should note is that when we talk about this, frequently we would say that the nitrogen is saturated with the MEK. When someone tells you that, like air is saturated with water, okay? Saturated with means that that next thing is going to be the one that could be in equilibrium with a liquid, okay? The MEK is in a saturated state. It's in both the liquid and the vapor phase. The nitrogen was not saturated vapor, it's a gas, or we can also call it a superheated vapor. Now this gives me a way that I can use Raoults Law as a way to define kind of mathematically what it takes to be a superheated vapor. A superheated vapor is one when the partial pressure is less than the vapor pressure at that temperature. So this gives me a quantitative way to define a superheated vapor. What we had before was a qualitative look at a graph. This is just simply an alternative. One last little topic that I want to address is the dew point. Frequently we're going to have problems when we talk about, the air being nearly saturated, they will, on the weather forecast, they will talk about what is the dew point. Okay? So if you have a superheated vapor that contains some gas that could condense, or some vapor that could condense, and you cool it just until that moment when the first drop of liquid appears, that's going to be called the dew point. And in that case, our equation, Raoults Law, is going to apply and be true for the dew point. One second thing, and this probably, the title for the slide is probably bad. Sometimes we're going to talk about a gas, and especially when you look at older materials, it's much more common for the old-timey engineers to say this, but they'll talk about a gas in terms of its degrees of superheat. Whenever they do that, all they are saying is that if you knew what the dew point was, it's that many degrees hotter, okay? So if you had something that had 5 degrees of superheat, and you knew that the dew point temperature was 28 degrees C, okay, and I'll call that 5 degrees C, then the actual temperature is going to be 28 plus 5, 33 degrees C. Okay, so it's a way of defining the temperature. It's just sort of a little awkward. But the advantage is that this can float with pressure changes a little bit. So as the pressure changes, the vapor or the dew point temperature will change also. Now, one final comment on dew point. If you have a pure substance, that dew point is exactly the same as the boiling point. Okay, this is the dew point, and this is the boiling point. For those two, for a pure substance, these are going to be the same. So this concludes this lesson. And the next lessons, we're going to look at other ways that we can describe vapor-liquid equilibrium that are slightly more rigorous than this one. And we'll continue with this study of vapor-liquid equilibrium in this course. And in future courses, you're going to go even deeper into that topic.